Now, we're used to thinking of acids and bases as a very set group of compounds, like acids are things like HCl, HNO3, but what we have just seen recently is that the conjugate bases of weak acids, or the conjugate acids of weak bases, are also acids and bases. And the reason why they're acids and bases is because they can react with water in a process called hydrolysis. In hydrolysis, these conjugate acids or conjugate bases react with water to produce hydrogen or hydroxide ions. For example, if we take a look at the fluoride ion, fluoride is the conjugate base of a weak acid, hydrogen fluoride, and since it's a conjugate base, that means it can accept protons. When it accepts protons, it forms hydroxide ions, which the formation of hydroxide ions is going to overall raise the pH of the solution. And so the existence of the fluoride ion will actually cause the solution to be basic. So these cations and anions that come from that are the conjugate acids or conjugate bases of weak acids or weak bases can cause solutions to be slightly acidic or slightly basic. These aren't strong acids or strong bases, they're very, very slight. So let's take a look at some solutions that do this. First off, remember that the conjugate acid or the conjugate base of a strong acid or a strong base has negligible acidity. That means that if you have a strong acid or strong base, the cations that come from them have absolutely no effect on pH. So what are some of our strong acids? Our strong acids are things like HCl, HNO3, H2SO4. The anions that result from this, Cl negative, NO3 negative, SO4 negative, or HSO4 negative, these are going to produce solutions that have no appreciable pH. So that means if I have solution of, let's say, NaCl, it's not really going to do much to the pH because its anion comes from a strong acid and its cation comes from a strong base. All right, if we have cations that come from strong bases like NaOH or KOH, these cations have absolutely nothing to do with changes in pH. Now, solutions that do affect pH are solutions that come from the conjugate base or conjugate acid of weak bases or weak acids. For example, if you have an anion that is the conjugate base of a weak acid, then this is going to produce a solution that is going to be basic because it's going to produce hydroxide ions. So if it has acetate in it, if it has fluoride in it, if it has carbonate in it, these are all conjugate bases of weak acids. If you have a salt which has a conjugate acid of a weak base in it, then it's going to produce an acidic solution because it's going to produce hydrogen ions. The main one of these that you're going to need to be familiar with is ammonium. That's the one that shows up the most. Another way of writing this equation looks like this. In this case, we include water in our equilibrium equation, so we have the formation of hydronium, but this is the exact same equation. Another substance that can undergo hydrolysis are salts that have pretty high charges on them, metallic ions that have high charges on them, like aluminum. Iron is another one that shows up. These will form complex ions with the water molecule, and the water molecule becomes highly polarized, and what happens is the hydrogen ions, or one of the hydrogen ions on these water molecules that get attached to the ion will become easily removable, and that's called the acidic hydrogen. This looks something like this. So the complex ion that is formed whenever the metallic ion attaches to the water, one of the hydrogens will just drop right off of it, and we'll get an acidic solution as a result. Now, if you have a combination of acidic and basic ions within a solution, really the only way to figure out what the resultant pH is going to be is if you have the actual Ka values to look at. If your K and Kb values. If your Ka value is higher than your Kb, it's going to be acidic. If the Kb value is higher, it's going to be basic. If they're the same, it's going to be neutral. Alright, so let's look at some examples of this. So we're going to list these solutions in order of increasing pH, and to do this we have to look at the anions and the cations that make them up. Now when looking at these, the first thing I do is I look for things that come from strong acids or strong bases, and I mark them out because they really have nothing to do with the pH. So I'm looking at barium, that's from barium hydroxide, which is a strong base. I'm looking at chloride, which is from hydrochloric acid. I'm looking at bromine, which is from hydrobromic acid, and I'm looking at potassium from potassium hydroxide and nitrate from nitric acid. So what I'm left with is acetate, which is the conjugate base of a weak acid. So if it's a conjugate base, it's going to form hydrogen ions, and so we're going to lower the pH. Oh, no, wait, I said that backwards. If it's a conjugate base, it's going to accept hydrogen ions, so it's going to produce hydroxide ions, so it's going to raise the pH. I've got ammonium, which is a conjugate acid of a weak base, so that's going to produce hydrogen ions, so it's going to lower the pH. I have an amine here, which is also going to do the same thing that ammonium did. And this one has nothing in it that's important. So my big question really is going to be which of these two is going to lower the pH the most, and the only way I'm going to be able to figure this out is to go look up the Kb values of these two substances. If I look up the Kb values for the bases that these conjugate acids come from, I notice that NH3 is the weaker of the two bases. Since it's the weaker of the two bases, that means its conjugate acid, NH4, is going to be the stronger of these two conjugate acids, so it's going to have a more of a lowering effect than the NH3CH3 is going to. So that means a solution made of ammonium chloride is going to have the lower pH. And then KNO3 is going to be a neutral solution. And then the barium acetate is going to have our highest pH. Section 1610 focuses on how structure affects acidity. And really this whole section is about making hydrogen ions. The easier it is to make hydrogen ions, the more acidic something is. So things that can affect this is the strength of the bond between the substance, whatever it is, and its hydrogens. The stronger the bond, the less likely it is to form hydrogen ions, so the less acidic it is. Another factor that's important is polarity. Whenever you have high bond polarity, you tend to have a greater chance of losing the hydrogens. It has to be polarized, this way, with the anion being much more polar than the hydrogen, so it pulls electrons away from it, and as a result it makes it much easier for the hydrogen ion to be removed from the anion. And then the third factor that's important is the stability of your anion that is being formed. The more stable it is, the stronger your acid it is. Now usually the strength of acid occurs as a combination of all three of these things. And so you can have something that has a strong bond but also a highly polar bond, and you'll end up with an acid that's not that strong as a result. HF is a really good example of that. It's a very polar bond, but it's also really strong. And so even though it's polar, you end up with a weak acid because of the high strength of that bond. For binary acids, which is just hydrogen with some other element, so HCl, HX, H whatever, the strength of the bonds is probably the most important thing. The strength of the bond tends to decrease as you go down the periodic table, and as a result, they become more and more acidic as you go down the periodic table. Another important group are the oxyacids. Oxyacids have a hydroxide group, sometimes more than one, and then a whole bunch of oxygen atoms all bonded around a central atom. the more oxygens you put around that central atom, the more acidic your compound becomes. Because if you look at your central atom, the more oxygens you add around it, the more those electrons are getting pulled away from the hydrogen. And when the electrons get pulled a whole lot from the hydrogen, it becomes much, much easier to remove that hydrogen from the anion. Another thing that can affect acidity of oxyacids is the electronegativity of X. As you increase that electronegativity, you increase that pull, and as a result, it becomes easier and easier to remove that hydrogen. It becomes more acidic. And then our last group are the carboxylic acids. Carboxylic acids all have this structure right here where you have some sort of organic group and then a carbon, double bonded oxygen, and then an OH attached to it. This hydrogen right here is your acidic hydrogen, so it's the one that's going to exit. So the more pull you can get this way, the easier it is to remove that hydrogen, so the more acidic it gets. So the more electronegative atoms you add to this side of our chain over here, the more acidic our carboxylic acid becomes.